Gauss quadrature is by another great mathematician, Gauss. So we can do more accurate integration with Gauss quadrature. With Newton codes, I said that with n points, we can get exact integral for function which is n minus 1th order polynomial. But with Gauss quadrature, Q, with n points, you can get exact integral for 2n minus 1th order polynomial. Okay, so it's really accurate. Okay, so let's begin. So this formula is exactly the same as before. So we have this function W, this weight W, and FC cells. In Gauss quadrature, idea is to get both xi and wi. They both are unknowns. So the idea is that for given endpoints, so these are the endpoints, so 0 to n minus 1. Given endpoints, we look for wi and xi so that our integral is as accurate as possible. Okay, so this is a complex method, and yeah, that's our idea. Okay, with endpoints. So how many constants are there? There are 2 n constants, right? So there are n xi's and n yi's or fxi's. Sorry, I should not say that. There are n xi's and wi's. Okay, we need to determine them. So let's take let's get our target set. So I want an exact integral for a polynomial of order 2n minus 1. That's my objective. Okay, so because 2n minus 1 polynomial will have 2n equations. Okay, so I'll just show you as an illustration first. Simple example. So let's do for n equal to 2. So how many unknowns will be there? There are 4 unknowns, wi and xi's. So my idea would be I should be able to get the integral exact up to 2n minus 1. Okay, so that will be 2 into 2 is 4 minus 1, so x cube. So I should get exact integral for any of this function. Okay, 1, x squared, x cube, or a combination. But these are like basis function. If you can get exact integrals for these 4 functions, then I know that a combination also will be exact. Okay, so we'll get 4 equations for them. Okay, so the idea is, so let's just put for fx equal to 1. So if I put fx equal to 1, the right hand side is what? It's just the w0 plus w1, right? Because the function value of the function fxi will be 1, 1. And what is the integral? My limits are 0 to minus 1 to 1. Okay, minus 1 to 1. So the a is minus 1 and b is 1. So integral will be 2, right? 1 dx from minus 1 to 1 is 2. So that is corresponds to 1. If I put x, okay, so I want to do minus 1 to 1 x dx. So what is the integral? It's an odd function, so it should be 0. No, it's just straightforward, is 0. But the right hand side will be wi fxi, so is w0 and w1, and the value of the functions is a linear function, so just x0 and x1. Okay, so this is second equation. Third equation is x squared. So x squared, the integral is x cubed by 3. Put this limits, so it's 2 by 3, and the right hand side is that. Fourth one is x cubed, so 0, and this one. Okay, so we have 4 equations. Now you can solve for these 4 variables, right? W's and x. So we can do this privately. So what turns out that both W's are 1, and the x0 and x1s are 1 by root 3 and minus 1 by root 3. Okay. So this is a simple example. I mean, this how, well, we don't compute this way, but this is a basic idea. Okay. Now, if you have more points, let's say we have 6 points. So we'll have 13 equations and pretty complicated ones, right? I mean, there'll be x naught to the power 13, not 13, x naught to the power, yeah, 13. 13 will be there, sitting there. Okay. So, and this will be too cumbersome. I mean, solving integral will be a headache. So Gauss came up with a very clever idea. So he suggests that we can use orthogonal polynomials, right? All of you are aware of orthogonal polynomials. Right? All the physics students should be aware of, physics and math students should be aware of orthogonal polynomials, and maybe some engineering students who are doing its elective, they may not know this. This is a definition of orthogonal polynomials. Okay, so we have lower limit a, upper limit b, and this is called weight function. And these are the polynomials. Okay, so we'll have n plus 1 polynomials. Okay, polynomials, and they satisfy this relation. So you take two different polynomials. Let's say phi 0, phi. So we denote them as phi 0 da 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 to phi n. If you take two different polynomials, multiply them, and multiply that with further h and integrate it. Oh, I forgot dx. Then this is delta function. That means this integral is 0 if they are different functions. If the same function, then the integral is not 0, and this is gamma I. Now, one example of polynomial is 1. So let's say 1x and 3 by 2 x squared minus 1. So there are three polynomials. Okay. Now we can work out, and the limit is minus 1 to 1. We take limit minus 1 to 1. So these are even and odd function that straight away 0, right? You can also show that these two are also, if I multiply, I get 0. Okay. So this in fact is a Legendre polynomial. So they are in fact infinite order. Okay, and there's a way to construct it. So this comes in quantum mechanics. In fact, this equation comes when you have this equation. Okay, Laplacian phi equal to lambda phi, and we encounter this in quantum mechanics, or in fact anywhere. I mean, not so wave equations. So we'll encounter this. So we'll do three polynomials in this class. So that will come a bit later. Okay, so let's just assume that these polynomials exist, which satisfying this property. Okay. Another function which is not polynomial, in fact, which is infinite order polynomial, but not polynomial this sort, is sin x. Okay, sin kx. Okay, k is in fact we can choose as okay, the better idea is sin is k is sin pi kx. Okay, 2 pi kx. So this one is for k is a integer. Then these are also orthogonal, right? Sin k 2 pi x is a orthogonal. So this Fourier series expansion. Now, but we're not doing it with this kind of functions. So, but we need polynomials, which are like real polynomials. Now, with these polynomials, what Gauss derived, I will go through the derivation, but I'm just stating the result first. So the weight. So remember the integral is wj fxj 0 to, I'm going to go up to n. Okay. So the weight, so this integral, in fact, this integral is hx is there also, hx fx dx. and limits are same limits as orthogonal polynomial. Limits are determined by the property of orthogonal polynomial AB and the weight function also. Okay, so this equal to this. Okay, so these are weight J's. Okay, so these are actually not n minus these n minus one, not n1. So these are xj's. So we need to get this xj's and weights. Now what are the xj's? Xj's are roots of the polynomial phi n. Okay, so xj's are roots of the polynomial, which we can, in fact, is tabulated, is there in people have already computed it, and the weight will be given by this function. Okay. So once we know the weight in this xj's, then we are in business. I mean, you can just compute this and we are done. Okay. So this is how we can compute the integral for any number of points. So that's the basic idea. And yeah, this is the integral. Now, the proof is a bit involved. So I caution you that you pay attention. It's in fact it's nice proof, excellent proof. Involves very beautiful mathematics. So I just want to take you through the proof. Now, I'll also show that this formula is accurate for polynomial up to 2n minus 1. Okay, that's what we wanted. With n points, I need to get polynomial which is good up to 2n minus 1, order polynomial. Okay, so the proof, there are 3 steps. So I will go through all, I mean, the step 1 and step 2 in some detail, but step 3, I will just state the result. So we have this fx function, but let's assume that it is polynomial of order 2n minus 1. Okay, so and I want to get exact integral for this. Now we already have chosen this polynomial, orthogonal polynomial. So phi 0 to phi n, right? So these polynomials are phi 0 phi n. So I take this function f of x, divide this by phi n x. So there will be a quotient which is after division. I mean, some part will come out as a quotient q n x, and some reminders. So this reminders. So so function f of x is basically qn minus 1 multiplied by phi n x plus rn x. And both qn minus 1 and rn minus 1 is polynomial of order n minus 1. Right? Is that correct? I mean, this function could be, let's say, x cube. I divide this by x squared minus 1. So there will be one x left, no? So one x will be left, and there will be a remainder, right? And you can just, this intuitive, I mean, there's no need to have proof. So what remains is the highest power minus highest power of this. Okay, is that everybody is happy with this? So this polynomial n minus 1, this is n, and this is n minus 1. Now let's do the integral. So hx, I just multiply by hx both sides and integrate. The first integral, this one, okay. So hx will be qn minus 1 phi n x dx. Now I'm claiming it is 0. You expand qn minus 1 in terms of orthogonal polynomials, okay. And this is polynomial of order n minus 1 will be some ai phi i's, okay. But we know that for sure that I is less than n minus 1, less than equal to n minus 1. Right? So I is less than equal to n minus 1. Okay. So, but all these phi's are orthogonal to phi n. As I said, I mean, if phi a, phi I, phi j, if I not equal to j, then it's a delta function. Or is in fact 0, sorry. If I not equal to j is 0. If I equal to j, then it is not 0. So what do you get as an answer? So I get this hx fx dx equal to this part will give you non-zero integral. Okay, so we have decreased the complexity. We are going from this at least one term I know that is 0. Okay, Abhay also says the orthogonal polynomial, great. Okay, so by the way, they're very, very useful. Now, orthogonal polynomial in physics, quantum mechanics is all about orthogonal polynomials. Okay, so that's step 1. Step 2, what is then step 2? So we go further. Now, this phi n, this highest polynomial in for my consideration, there are n. So there are n minus basically. Yeah, so this is the highest polynomial I'm considering for n points. So it will have zeros. So these zeros are xj's. Okay. So let's say polynomial is x squared minus 1. Okay. So how many roots are there? There are 2 roots. Right? So plus minus 1. So this there will be n roots. This is a fundamental theorem of algebra. Okay. So I'm just give a very simple example, but this phi n has n roots. So we take those roots as xj's. Now, again, the same. Remember, I had expanded f of x in terms of this polynomials. So fxj is, so instead of x, you substitute xj, any root. So I get qn minus 1 xj, phi n xj plus rn minus xj. Now what happens to this term, first term? Is 0, right? Because phi n xj is 0. Xj is a root. So please remember, phi n xj is 0. Okay. So fxj is nothing but rn minus xj. So all my complexity of integration is falling into this function. Okay. In fact, we are almost there with the final, almost there with the semi-final. We'll reach semi-final soon. So r minus 1x, I'm going to expand in terms of Lagrange polynomial, which we did in the previous last week. So this is Lagrange polynomial, but these Lagrange polynomials, I'm using this xj's for constructing the Lagrange polynomial, right? So remember we had product x minus xj divided by x minus xj, right? That kind of thing. Now, so what do I choose for this xj's? I should choose the roots of this polynomial phi n. So this is how this this guy is coming in this constructed. Now, so I multiply Lxj into Rn minus 1 xj. So I'm just expanding Rn minus 1 xj in terms of Lagrange interpolation, Lagrange interpolating polynomial. Okay, so remember I used to write fx as one of the polynomial p2x, right? So this was approximated as p2x or pnx, and that was this Lagrange polynomial and yj, Lj yj. Okay, so yj is nothing but value of the function at that point. So that's what I got it. But by using the previous step, remember this one is same as fxj. So I have this equality. So great. Now let's integrate both sides. And in fact, I wanted that, no? So integral a to b hx fx dx is same as I'm rewriting this fxj here is, so yeah, so let's write this as rn minus 1 xj, r minus 1 x, not xj, right? We did in the previous slide. Now this integral will be, so hx r minus xj. So now when I integrate this, in fact it comes down to basically integrating this. So I put hx here and dx here. Yes. So right hand side will also involve integral hx dx. Fine. So this is what I have written here. So fxj will come out hx ljx dx. Correct. So in fact we are getting the same form as what we wanted to derive. So this object is a weight. This is Wj, this is W, and Fxj, right? We obtained the weight, all the weights. So I have the roots as well as the weights. Okay, so I'm done. I mean, my work is over. But problem is this computing this integral itself is a challenge. I would like a simpler formula than this. So Hx is known, but I need to compute the integral. Okay, it is possible to do it, but to compute one integral, I don't want to do another integral. In fact, many of them. For every j, I have an integral. That's too much work. So we need to simplify computation of Wj. But we have the formula. Okay? And this formula is accurate for polynomial of 2n minus 1. Like integral will be exact for polynomial 2n minus 1. You see, in this derivation, there was no approximation made. Now, the next step, which is step 3, I'm not going to do all the algebra. Is there in the notes which I sent you. So this weight, okay. Now this Lj which we have constructed with Lagrange interpolating polynomial can be written like this. Okay, a proof is there in the notes. You can find the proof, and then this can be further simplified. So my objective is to remember that I need to compute this. And it turns out you do a lot of algebra like that, and in fact some theorems as well. And this integral happens to be that. Okay, so gamma n, remember, it is a coefficient of the orthogonal property polynomial. So gamma n is integral hx phi n squared x dx. So this is gamma n. Okay, n is a coefficient, I have written it here, of xn in phi nx. So phi nx, when I expand, there could be an x to the power n. Then after that, lower order polynomial. So this is an. And these are just derivatives, phi prime first derivative, and this is phi n plus 1. Okay, so this was done by Gauss. Okay, so this really using a lot of analysis. Okay, this field is called analysis. You are dealing with functions, continuous function, derivatives, and so on. So this is using analysis really well.